Hello, my name's Tony Rogers. I'm a graduate student in space plasma physics at the University of New Hampshire, and I'm here tonight to talk to you about space weather, winds, storms, and how they affect us here on Earth. I'm sorry I can't be there in person tonight, but hopefully you guys enjoy the presentation nonetheless. First of all, space weather. Question I get asked a lot is, how can there be space weather in space? Isn't space a vacuum? How can there be any weather if there's nothing up there to move around? Well, the answer is, there is stuff up there to move around. There are winds out there. There are storms. And all of these things, just like regular thunderstorms here on Earth, have a real effect on property and infrastructure here on Earth, to us. In order to understand these things, though, we really need to first understand something called plasma. Now, plasma is not like the blood plasma that you go in and you donate at the office or anything like that. In this case, plasma is a hot, ionized gas. It's actually the most common form of matter in the universe, more common than solids or liquids or anything like that. It is found everywhere. 99% of the observed matter in the universe is a plasma. It's what makes up the sun. It's also what's inside all of your fluorescent light bulbs, and it's what we're going to be talking about here today. Thinking about it as a fourth state of matter, let's review what the first three are. To begin with, we have a solid, where all of the atoms in a material are all locked together in a very rigid pattern, like, for example, a crystal or some other very rigid alignment. And while they have some heat, they're going to be jiggling around a little bit. Because really, when you think about it, heat is just the collective general jiggling around or wiggling of particles. And so every solid that isn't at absolute zero is going to have a little bit of wiggling in the atoms, but with a solid, it's not so much that it can't hold its shape. Now, if we take this solid and we keep adding more and more heat to it, and the atoms are jiggling around more and more and more and more, eventually they can't hold together in that rigid structure anymore, and they all fall apart into a pile. And now we have a liquid, where all these same atoms are still sitting there, they're still collected in a pile, and they're all still jiggling around, but they're all at least hanging out together at the bottom of our container here. But if we keep adding more heat, if we add more and more heat, and they jiggle around more and more and more, then eventually they're not really sitting in a pile anymore, and instead they're bouncing off all of the walls. And now we have a gas. It's the same material. These are the same atoms as we started with in our solid, but now they're all bouncing around like a gas. Now, in order to talk about a plasma, we need to go even smaller. And looking inside one of these atoms, here we have the nucleus, and we have the positively charged protons, and here we have the neutrons, and then some electrons that go orbiting around the nucleus. Now, as we've been adding heat and the atoms have been jiggling around, all of these particles inside of each atom have also been jiggling around and moving. And the protons and the neutrons and the electrons, they all keep jiggling, and as we add more and more and more heat, all of these things are going to be moving more and more and more. And especially these electrons. They're going to be wiggling around and orbiting wider and wider and wider until eventually, whoo, off one of them will go. Just decide, nope, I'm out of here. I got too much energy. I can't stay confined anymore. And off it goes. Now, this means that instead of having just three states of matter, we have four. We have the solid, where all of the atoms are locked together in a rigid structure. And then as we add more heat, we have a liquid, where they're jiggling around, but they're at least still held together. And then we have a gas, where they're bouncing off all of the walls. And then we have a plasma, where the positive nuclei and the negative electrons have got so much heat they can't even hold together themselves anymore. Now, in order to maintain a plasma, we either need to keep this material, all these atoms, very, very hot, or we need to have the pressure very, very low, which means that there's just not a lot of stuff out there, meaning that once these electrons get kicked loose from their nuclei, they aren't going to run into another nucleus anytime soon and get captured and become a whole atom again. In space around our Earth, in a vacuum, the plasma has very, very low pressure, and while some plasmas may also be very hot, all of them outside of the sun has a very, very low pressure. The sun has a very, very high temperature, and as you get closer to the surface, the pressure also goes up a great deal. Now, coming back to the solar wind is made up of this plasma coming out all of the time. On the right here, we see a picture taken by Michael Adler of the solar eclipse just a few years ago. And here you can see the streams of the solar wind coming off of the sun and streaking out all of the time. And this is a picture of what the solar wind looks like as it comes off the sun while the sun rotates around. But why does it necessarily come off more one place than another? Well, the sun has a magnetic field. And in fact, that magnetic field is generated by the rotation of the sun. As the sun rotates around, the plasma that's up inside of it, because it's separated electrons and positive nuclei, that means that it's a bunch of charges moving around. And whenever you have a moving charge, you create a current. And when you create a current, you create a magnetic field. This whole thing is called the dynamo effect. And what it generally makes is, under ideal conditions, this rotation of the sun's plasma creates a magnetic field kind of like a bar magnet. Just loops coming in and out. Life is good. However, the sun actually rotates at different rates, whether you're at the equator or up near the poles. Down here at the equator, the sun rotates on a period of about 25 days. But up near the poles, it only rotates on a period of about 31 days. And this difference means that over time, the plasma and the magnetic fields get twisted all around as the sun is rotating around. And on the inside, this happens even faster because the sun also rotates at different rates depending on how far deep into the sun you go. And so, as the sun is rotating around, the magnetic field gets all twisted up and tangled. And as it gets tangled, these little loops of magnetic field start popping up out of the sun. As the sun keeps rotating and the plasma keeps moving, those loops continue to grow. And those loops turn into sunspots. What those sunspots are little holes in the atmosphere of the sun caused by these loops of magnetic field poking up and through it that allows some of that plasma, it's sort of like a highway for that plasma to come out and go spraying out everywhere. The sun's magnetic field gets all tangled up like that about every 11 years, and after a while it gets so tangled up that everything just sort of resets and it straightens itself out again. Like I say, this cycle happens on about an 11-year cycle. The more tangled up it gets, the more of those loops we get, and the more of those loops, the more sunspots we get. And people have been observing this for hundreds and hundreds of years. This is a figure that shows the number of sunspots that have been counted on a fairly regular basis ever since the 1600s. And for that matter, we have records of the Chinese observing sunspots back to almost 2,000 years ago. But wait, weren't we talking about the solar wind? Now, that magnetic field around the sun usually holds all of the sun's plasma pretty close to the surface of the sun. But all of these loops and holes in these sunspots let the plasma out and get away. Now, a little bit of it gets away all of the time, but the solar wind usually is caused by when much greater amounts get away from the sun, usually through these sunspots and other means. Now, the Earth has a magnetic field as well. In fact, a lot of planets in our solar system do. Earth, Mercury, Jupiter, they all go through the same process where their molten cores, the metal that's inside of the Earth and these other planets, as it's turning around, it does the same thing as the interior of the sun does. It creates a dynamo that generates the magnetic field. And just like the sun, after a while, that magnetic field starts getting tangled and twisted up. With the Earth, however, it's a lot more stable than the sun, so it only happens about every 50,000 years or so. Fun fact, we're about due for us to get all tangled up again and for the magnetic poles of the Earth to reverse, just like they do on the sun every 11 years. But I wouldn't worry about it too much just yet. Now, magnetic fields and plasma, they push on each other. Charged particles moving through a magnetic field are going to be pushed around by the magnetic field. And as we talked about before, whenever you have a charged particle moving, that generates a current, and a current will also modify a magnetic field. So, the Earth's magnetic field will interact with all those charged particles, with all of that plasma coming off of the sun, causing the solar wind and the Earth to push on each other. And it ends up looking something like this. The Earth's magnetic field, again, you can think of it kind of like a bar magnet just stuck through the center of the Earth. And usually it makes these normal sort of Dumbo ear kinds of shapes of magnetic field lines like you're used to seeing from school with a magnetic field from a bar magnet. But because the solar wind is pushing constantly on it, it means that on one side, all of this magnetic field in that sort of Dumbo ear shape gets squished in towards the Earth from the sun. And then on the side facing away from the sun, that same magnetic field gets stretched out into something we call the magnetotail, because it kind of looks like a long tail when you zoom out a little bit and look at it. Now, as I said, the magnetic fields in the plasma, they push on each other, and this includes the solar wind. The faster the solar wind is, the more the Earth's magnetic field gets squished on the front and stretched out in the back. Now, when you start moving around the magnetic field like this, it will store energy in the magnetic field, kind of like with a rubber band. If you squish up a ball of rubber or you stretch out a rubber band. When the sun is quiet, the field relaxes, and it's sort of like easing up off of letting a rubber band unstretch gently. But storms can happen sometimes. Solar storms, where big magnetic holes let lots and lots of plasma out all at once. This, by the way, is an actual image taken from the Solar Dynamic Explorer. This is another image taken from the SOHO satellite, and down here you can see a whole bunch of plasma, what's called a prominence, coming off of the sun. And to give you a sense of scale for how big this is and how much energy and plasma we're talking about, that is Jupiter. And that little spot way down there, that's the Earth. Flares and other events like prominences can release lots of hot, dense, fast plasma from the sun, usually in the form of what's called a coronal mass ejection, or a CME, which is kind of like a big cloud of this plasma coming off of the Earth and moving outwards in the solar system. These happen most often when the sun's magnetic field is super tangled up, when there are more sunspots that it's more likely to happen. And so at the solar maximum, when there are the most sunspots you're going to see in a solar cycle, that's when we're going to see the most number of these CMEs and solar flares. Now, this ends up having this sort of a look where the sun spews out all of this solar wind and all of this and a CME, a big cloud of hot plasma, come towards the Earth, and then it interacts with the Earth's magnetic field. The plasma from the CME then pushes even harder than normal on the Earth's magnetic field, which leads to even more squishing on the day side and stretching out on the night side. And some of the plasma from the sun gets trapped inside the Earth's magnetic field. You can see here where, because of the way the Earth's magnetic field works, there's a little bit of a hole up near the poles. We call this the cusp. And some of the plasma from the solar wind can come straight down from the cusp. And this is one of the reasons why, for example, if you're in an airplane and you're flying over the North or the South Pole, you actually get a little bit more radiation than you do otherwise, because we're less protected from the solar wind up near the poles. Here we have a movie, which I fear is being a little glitchy as it plays, but here we have the sun zooming out, all kinds of the solar wind, and here's a CME coming crashing into the Earth from the sun. And you could see how the force of the CME and all of that plasma is sort of peeling away at parts of the Earth's magnetic field on the day side, and then pushing all that magnetic field strength on over to the night side. And then on the night side, it means that everything gets squished together until there's what's called magnetic reconnection, and magnetic field lines in the night side end up connecting together and then releasing that energy back in towards the Earth. And that's exactly what magnetic reconnection is, when the magnetic field is stretched or squished so much that it snaps, like when you let go of a stretched out rubber band, and all that energy comes snapping back. On the day side, reconnection means that the magnetic field gets peeled away, or alternately, that it's able to start pushing back against the solar wind. On the tail side, that reconnection means that the magnetic field snaps in towards the Earth, bringing plasma and energy with it. And all of this happens very, very quickly. Substorms are when that trapped plasma moves within the magnetic field. On the day side, these substorms can affect satellites and radio waves. On the night side, these substorms create the aurora and so much more. Now, as for the aurora, sometimes these are called the northern lights or the aurora borealis. And all of these lights are caused by energy. Energy coming back along the tail and moving in towards the Earth, and then running into the upper atmosphere, causing the upper atmosphere to light up like a light bulb. So this is all from particles and plasma coming down the magnetic field lines and then running into the Earth's atmosphere and lighting it all up. And just because I think these things are absolutely gorgeous. The different colors are caused by higher energy or lower energy particles in the plasma running into the Earth's atmosphere and then smacking into different kinds of elements in the Earth's atmosphere, whether it be nitrogen or oxygen or other things. And here's a view of the aurora from space. Absolutely stunning to me. Now, as cool as the aurora are, it isn't all sunshine and nighttime rainbows. Plasma comes down the middle too, coming down through the center of the tail straight towards the Earth. And as it comes, it's being accelerated and heated all the way. So all of that already hot plasma that came from the sun and got trapped inside the Earth's magnetic field is now getting heated up even more as it sucks up some of that energy from the snapping rubber band of the Earth's magnetic field contracting. This adds all kinds of new particles and energy to what are called the radiation belts, also called the Van Allen belts after James A. Van Allen. These are rings of very, very high energy plasma that have gotten trapped in the Earth's magnetic field fairly close to the Earth. Now, the inner Van Allen belt, or the inner radiation belt, lots and lots of protons and other heavy ions that had enough speed and enough mass that they could get really, really close to the Earth before they got trapped by the magnetic field. These belts, especially during storm times, can overlap with low Earth orbit. And so these are the belts that are the most of concern. They're the greatest concern to both satellite operators and to astronauts. Now, these outer belts are sort of two-thirds of the way, halfway or two-thirds of the way between low Earth orbit and geosynchronous orbit. Most of the plasma in here is made up of electrons, energetic electrons, which we also call beta radiation. During storm time, oxygen, energetic oxygen, and other heavy ions, in terms of that have been ionized and become plasma and become very energized, also get added to these radiation belts. And on top of that, this outer ring can expand outward and can sometimes overlap geosynchronous orbit, endangering the satellites that are in orbit there. Now, the Van Allen belts are also part of a system called the ring current. And these ions, mostly the hydrogen and oxygen, are orbiting around the Earth between some of the radiation belts. As these are orbiting around, again, they're charged particles, which means as they move, they generate a current. The current that these generate creates a magnetic field that weakens the Earth's normal magnetic field. And all of this happens during storm time. So it's almost like the storm is conspiring. Not only is the solar wind coming and squishing in at it from the day side, but also all these particles getting accelerated in from the tail are causing the Earth's magnetic field to weaken even further. Part of that disturbance of the Earth's magnetic field can also cause rapid changes and fluctuations in the Earth's magnetic field, which can occasionally cause compasses to be slightly less accurate. In fact, very precise compasses were used 300 years ago in order to watch as solar flares and as CMEs came and impacted the Earth. Now, the rapidly changing magnetic field, for example, as the tail contracts in during substorms, this can create a current along the Earth that can be absorbed by any wire on the Earth. And yes, I mean any wire. every wire on the Earth, the longer the wire, the more of this electricity it's going to absorb from the changing magnetic field. This especially means things like power lines, telephone lines, and all kinds of things like that. Again, the longer the wire, the more electricity it's going to absorb because of this changing magnetic field. A really extreme version of this happened in 1859. There was a massive solar flare observed by a British astronomer named Carrington. And about a day and a half afterwards, separately was recorded that telegraph lines all over the world, because the telegraph was just starting to really make a big impression, went into chaos. Usually telegraphs were operated by taking a battery and connecting it onto the line so that you could, and then using the telegraph key to switch the current on and off, thus creating a signal for Morse code. However, during this Carrington event, for about 2 days, some telegraph operators reported being able to unplug their batteries, not have any power going to the telegraph cables at all, but they could still use them because there was so much electricity just running along the wires. For that matter, there was so much electricity that one operator, as he was trying to disconnect his telegraph assembly, got shocked badly enough he had to go to the hospital. Now, these kinds of storms are happening all the time. We haven't had a storm as bad as the Carrington event for many, many, many years. However, there are still storms going on all the time. And in fact, we're just at a point where we're starting to go into a new solar cycle. We're at the beginning of solar cycle 25, just about a year into it. And so here over the next, about 4 or 5 years, it's going to keep getting stronger and stronger. And about 4 or 5 years, it's going to hit maximum. So now is a really great time to start thinking about doing some solar observing and watching out for solar storms and space weather yourself. There are some websites that can help with this. Websites like The Sun Today, which has lots of pretty pictures, and a NASA scientist is actually the one who runs it in their spare time. Spaceweather.com is for amateur enthusiasts, but it still has a lot of really great information. AuroraWatch.ca is a Canadian website run by the University of Alberta. And as the name implies, it is really focused on just observing the aurora and understanding the aurora. It's a really great place to go if you want to find really great aurora pictures or to get a better sense of when we may be able to see aurora down in New Hampshire. Also, there's solarham.net, which is focused on amateur radio. Now, just as all of these solar conditions can generate light and can potentially interact with satellites, they also affect how radio waves bounce off of the Earth's ionosphere. And so amateur radio operators are very, very interested in space weather, what it's doing, and how that may affect their own radio communications. And solarham.net is a very good website for looking at space weather from that perspective. Also, a really great book is written by Jack Eddy, The Sun, the Earth, and Near-Earth Space, a guide to the Sun-Earth system. It is actually a free book originally commissioned by NASA to be given out to senators and government representatives. And he ended up writing it so long that they said, well, we can't just give this out to senators. They'll never read it. And so instead, NASA publishes it for free. And you can download a free PDF of it or download it to your Kindle for free at that website I have shown there. They will also provide links there if you want to purchase a printed copy of the book for, frankly, not very much. Other things you can do in order to watch space weather at home. There are plenty of maker projects, for example, Arduinos and things like that, to set up a magnetometer, basically a really fancy compass for measuring and watching the magnetic field move around as space weather is impacting the Earth. You can also track sunspots. You can observe the sun, as long as you do so safely, and graph where the sunspots are. This can be done with decent binoculars or a small telescope, so long as you have a proper filter. Do not go looking at the sun without a proper filter. You can also watch for aurora. Aurora aren't super common in New Hampshire, but they do occur when there's a moderate storm, by which I mean a KP index of 7 or more, and you can find out more about KP indices on some of the websites from the last page. Lastly, if you're interested in how space weather can affect amateur radio communications, different stations from around the world can talk to each other depending on what space weather is doing. And in terms of identifying how this works and really measuring scientifically how all of that is done. A group called hamsci.org is doing a lot of great work with that, and with projects to build home magnetometer kits to be able to measure a lot of this kind of stuff. And that may be somewhere else for you to look. Thank you very much for your time. Again, I'm very sorry I couldn't be there in person, but hopefully you enjoyed this and got some good information out of it. Thanks, and have a great night.